High in Oregon's Cascade Mountains lies a breathtaking lake that looks impossibly calm. The water is still. The cliffs are silent. There are no warning signs that anything here is wrong. But this serenity is deceptive. Beneath the surface lies a vast collapsed volcanic system, part of an active tectonic arc that continues to shape the Pacific Northwest. Systems like this do not go extinct. Pressure does not disappear. It shifts and accumulates. And when conditions change, places that appear peaceful can awaken with little warning. Today, let's delve into Crater Lake and its hidden dangers. Crater Lake sits within the Cascade volcanic arc, a chain of volcanoes stretching from northern California to southern British Columbia, formed by the Juan de Fuca plate sinking beneath the North American plate at the Cascadia subduction zone. As the oceanic plate descends, it releases water into the mantle, lowering melting temperatures and generating magma. Over millions of years, that magma has repeatedly risen toward the surface, feeding volcanic systems across the Pacific Northwest to this day. Crater Lake represents one of the most extreme outcomes of this ongoing tectonic process. Rather than sitting inside a typical volcanic crater, the lake occupies a massive collapsed caldera about 8 kilometers wide. This caldera formed when Mount Mazama, a massive 3,700-meter stratovolcano that once dominated the region, catastrophically failed. Mazama's importance today lies not in its gradual growth, but in the sudden manner of its destruction. Around 7,700 years ago, a powerful explosive eruption rapidly drained Mazama's magma chamber. As magma was expelled, the chamber roof lost its ability to support the mountain above. Instead of blasting apart, the summit collapsed inward. Huge sections of the volcano dropped into the emptying chamber, triggering further explosions as collapsing rock interacted with hot magma. This process created the Crater Lake caldera, a structural collapse rather than an explosion pit. Over centuries, rainfall and snowfall slowly filled this deep depression. With no rivers flowing into or out of the basin, the lake stabilized naturally, becoming the deepest lake in the United States, plunging to nearly 600 meters, and one of the clearest lakes on Earth. Crucially, this geology is not merely a record of past violence. Calderas are zones of long-term structural weakness, where the same fractures that enabled collapse continue to act as pathways for heat, fluids, and magma. Beneath Crater Lake's tranquil surface lies a volcanic framework that still shapes what this system may be capable of in the future. Before we continue, don't forget to click on that subscribe button and like this video, as it's the best way to support this channel. In the centuries following the caldera collapse, volcanic activity continued inside Crater Lake. Lava erupted onto the caldera floor, forming new vents, domes, and cones. The most visible example is Wizard Island, a cinder cone that rises above the lake's surface and clearly shows that magma continued to reach the surface after the catastrophic eruption. Additional volcanic features lie hidden beneath the lake's surface, including submerged lava domes and small volcanic cones revealed through bathymetric mapping and geophysical surveys. These features demonstrate that post-collapse volcanism was not a single isolated episode. The system remained capable of generating magma and transporting it upward through a crust weakened by collapse. This behavior is typical of large caldera systems. Collapse temporarily relieves pressure, but magma generation at depth continues. Over time, new magma can intrude into fractured rock, exploiting faults created during earlier eruptions. Activity may become smaller, more localized, and less frequent, but it does not necessarily stop. Crater Lake's history points to a volcanic system that remains active beneath the surface. Although no eruptions have occurred for thousands of years, long periods of silence are common in large volcanic systems. Geological timescales extend far beyond human experience, and quiet alone is not evidence of extinction. What matters is whether the internal conditions that allow magma to exist and move are still present. Beneath Crater Lake, they are. Crater Lake does not produce frequent large earthquakes, but it is not seismically silent. Since 2020, modern seismic networks have detected occasional low-magnitude earthquakes, typically below magnitude 2, occurring beneath Mount Mazama and in the surrounding region. Most are too small to be felt at the surface, but their location matters. In volcanic systems, even minor earthquakes can signal changes deep underground. These events are generally interpreted as the result of stress adjustments within fractured rock, the movement of hot fluids, or subtle shifts along faults created during the caldera's collapse. In some cases, short-lived clusters of earthquakes have been recorded, a pattern that volcanologists watch closely because swarms can reflect pressurized fluids or magma slowly migrating at depth. Crucially, this seismicity does carry a clear message. The system is not dormant in a mechanical sense. Crater Lake remains thermally and structurally active below ground. In volcanic terms, this kind of quiet seismic behavior often marks a system that is stable for now, but still capable of change. Volcanic eruptions are not spontaneous events. They are the result of processes that unfold over time, often deep below the surface. At Crater Lake, the most likely trigger for renewed activity would be the intrusion of new magma into the existing system. Fresh magma entering the crust increases pressure, heats surrounding rock, and releases gases that seek pathways upward. As pressure builds, fractures may open or reactivate along existing faults created during the caldera collapse. Earthquake swarms can accompany this process, marking the movement of magma or fluids through the crust. Gas accumulation plays a critical role as well. Volcanic gases expand as magma rises, and if they cannot escape gradually, pressure can build rapidly. One factor that makes Crater Lake particularly dangerous is the presence of a large volume of water directly above potential eruption sites. If rising magma interacts with lake water, it can trigger phreatomagmatic explosions, violent eruptions driven by the rapid conversion of water to steam. These explosions can occur with little warning and are capable of generating powerful shock waves and base surges. Importantly, none of these triggers require the buildup of a massive magma chamber like the one that existed before the Mazama eruption. Smaller intrusions can still produce dangerous, localized eruptions. The question is not whether the system could produce magma again, but under what conditions that magma might reach the surface. If Crater Lake were to erupt again, the most likely scenarios involve moderate explosive activity, rather than a cataclysm on the scale of Mount Mazama's collapse. An eruption through lake water could generate violent steam-driven explosions, sending ash high into the atmosphere and dispersing it across southern Oregon and beyond. Even a relatively small eruption could disrupt air traffic, contaminate water supplies, and damage infrastructure. Ashfall would pose a significant hazard to forests, agriculture, and human health. Lahars, volcanic mudflows formed when ash mixes with snow or heavy rain, could travel down valleys, threatening areas far beyond the caldera itself. The shock of an eruption in a national park known for tranquility would amplify social and economic impacts, particularly in a region dependent on tourism. For much of this discussion, the possibility of a catastrophic eruption looms deliberately large. The geological history of the site demands that level of seriousness. However, evidence suggests that a Mount Mazama-scale eruption is unlikely under current conditions. The magma system beneath Crater Lake today appears smaller, cooler, and more fragmented than the one that fueled the caldera-forming eruption. This does not mean the risk is negligible. Smaller eruptions can still be devastating, especially when water is involved. The danger lies not in repeating the past exactly, but in underestimating what a lesser eruption could do in a modern, interconnected world. Crater Lake is monitored by scientists using seismic networks, satellite measurements, and geochemical analysis. Any significant change, such as increasing earthquake activity, ground deformation, or shifts in gas emissions, would likely be detected before an eruption occurred. The warning window might range from weeks to months, depending on how rapidly conditions evolved. Preparedness remains a challenge because public perception of risk is low. Crater Lake does not look dangerous. Its beauty works against it, fostering the assumption that nothing dramatic could happen there again. Yet geology does not respond to human expectations or visual cues. The long-term outlook for Crater Lake is one of low probability but high consequence. Eruptions are rare, but the system's history proves they are possible. Crater Lake stands as a reminder that Earth's most destructive processes often leave behind its most beautiful landscapes, and that beauty should never be mistaken for safety. What we see today is a pause, not a conclusion. The lake is calm, the system beneath it is quiet, but the forces that once erased a mountain remain part of the same planet, operating on timescales far longer than human memory.